Dr. Christopher Quigg is part rock star, part hero, and part physicist. He's been in the lab slightly less than 50 years, but I'll leave it for him to address when he actually arrived. He's led our theoretical physics department in some key formative years. So the Fermilab theory department, where theoretical physicists join the laboratory for periods of time, is very famous. So the outgoing Secretary of Defense, Ashton Carter, spent time at Fermilab in the theoretical physics department. So that gives you a measure of the reach of that organization, as well as, directors of laboratories in other countries have all spent time at Fermilab. And that's really been through part of Chris's visionary leadership to create an environment which brings the best and then sends them on to the best. So Chris studied at Yale University. He earned his PhD at some other school in California, not called Stanford. I think Berkeley, that was it. He was at Berkeley. His work on super collider physics and the Higgs boson has been recognized with one of the highest prizes from the American Physical Society, the Sackharov Prize. But I would say what sets him apart from most of his colleagues is not his intellectual prowess, but more importantly, his ability to communicate his passion and his sincere belief that science and physics and particle physics can help reveal the deepest secrets of our universe. So without further ado, let me introduce Dr. Christopher Quigg. Thank you. Sir.
Thank you, sir. Thank you for coming tonight. It's a great pleasure to be with this audience. All of us think of ourselves as explorers, and explorers need support, of course, financial support, but even more important, being able to come home from our voyages and share our discoveries with people. And we've had the pleasure over many years of doing that with this audience in the Fermilab community. So I thank you for being part of that. It makes our work meaningful. So 50 years ago, this 6,800 acre site on which we find ourselves looked like this. There were the 400 residents of the planned community of Weston on the east side of the laboratory, many farm families who had settled here and tilled the soil, the Illinois soil, for many years. And it's very different now. In the space of a few short years, it became an international destination for physicists, welcoming scientists from all over the world and producing results that are valued by people all over the world. It's also named, as you've just heard, for Enrico Fermi, the Italian-American physicist, who was revered by all of us. He died in 1954, so he never got to see Fermilab, nor did we benefit directly from his input. But he was someone that we call the last universal physicist. He was a master of both theoretical physics and experimental physics. And this is something, he knew all the subjects of physics and was able to communicate and teach them. So he's been one of my personal heroes, and it is wonderful for me, and I think for my colleagues, to be at a laboratory that bears his name. The founders of our laboratory, Bob Wilson and others, wanted this to be a quintessentially American laboratory, but open to the world at large. And one of their first acts was to honor the legacy of what had been here before. So you see on the east side of the laboratory in a circle, sock circle, a number of the original farmhouses. Several of them are gathered together here in the building that we call Aspen East, which has served as a dormitory for many years. The little houses in the village of Weston have been used as dormitories or residences for visiting scientists, originally for labs and office space in the early days. And the roads in the east side of the laboratory in the Fermilab village have been named for some of the Native American tribes who were inhabitants of this area even before the Europeans came. Our founders made no little plans. This is an early scheme in which you see the village on the right, the big ring there, which is nearly 4 miles around, 2 pi kilometers around, was the sketch of the accelerator. And over time, this plan has evolved and been put into shape. And this is the conception of the laboratory now. You see that it bears the same outlines as the original, but with a number of very important additions that point to our present and our future. Now, Fermilab was founded at a time when the national instinct to get together and to do complicated, difficult, expensive things for the common good was much in evidence. So that was good. It was also a time of social upheaval. It was a time at which the nation was coming to terms with its legacy of segregation in the past. And the funding of the laboratory was threatened by the fact that the state of Illinois and the surrounding communities had not yet adopted open housing legislation. Our founders, Bob Wilson and Ned Goldwasser, his deputy, both by that exigency but also by personal conviction, wrote this statement of human rights for Fermilab. It says, in part, it will be the policy of the National Accelerator Laboratory to seek the achievement of its scientific goals within a framework of equal opportunity, employment opportunity, and of a deep dedication to the fundamental tenets of human rights and dignity. And then skipping over here, in any conflict between technical expediency and human rights, we shall stand firmly on the side of human rights. So that's been a beacon to us for all of this time. They didn't just talk or write. They also put their ideas into action. And one of the first actions was to find a group of young men in Chicago who had demonstrated a technical aptitude to bring them to the laboratory and begin training them to be technicians, eventually engineers, and so on. Part of their training took place at the Oak Ridge National Laboratory in Tennessee. And here they are on the tarmac, I guess it must be at Midway Airport, about to board their flight to Oak Ridge for the beginning of their training. Many of these people have been with us for decades, and all of them are among the billers of the laboratory. Wilson was a man who was born in a place that he called Frontier, Wyoming. No one knows whether it actually exists or not. And he wanted, again, this to be an American laboratory, so he imported 5 bison, to which the state of Illinois added a few other very early on. And as often happens when you try to do something interesting and good, it has unintended consequences. So the urban or maybe suburban legend grew up that the buffalo were actually here as canaries in a mine. There was no internet in those days, but had there been an internet, you would have read there that they're very sensitive to radiation, and when they detect radiation, their hair falls out. If you come back in the late spring, when they're shedding their winter coats, you'll find that all of their hair falls out. So don't be frightened by that, and come and enjoy our buffalo. So here was the groundbreaking for the main ring, our 2 pi kilometer around ring. You see everybody was there. Everybody's wearing hard hats except the boss. Everybody has a big clunky shovel instead of the boss. The boss has a gold-plated or maybe brass-plated shovel. If you'd like afterwards to come up and take a selfie with Wilson's shovel, please feel free, but don't harm anybody around you. And my chief operating officer will be happy if you wear a hard hat while doing that. So there it was. That was the beginning. I came here as a visitor. I was a fresh PhD, and I came here for a week in the spring of 1971, and I remember 2 things. One is that there was a lot of mud, and the second was that it seemed like a very exciting place. So now we look at the chain of accelerators. The first big piece of the accelerator was a reincarnation of one of the earliest accelerators. It's called a Cockcroft-Walton machine. This was the machine in England that was actually first used to artificially disintegrate the nucleus, and it still, until recently, served as the first stage of the accelerator at Fermilab. It's a very efficient way of getting up to a few tens of thousands of volts. Next comes the linear accelerator. So there it is. He's actually cleaning, not sleeping. It's called a linear accelerator because it's in a straight line. That's the second stage of the acceleration. Then comes the booster accelerator, which is just behind us out the back, which takes the protons up to about 8 billion electron volts. Here's some components of that being installed. You see lots of people doing lots of hard work in those days, and you saw some mud. Here's the main ring tunnel being finished. Again, lots of mud. This was done by cutting the ground away, so digging the ground away, installing a concrete flooring, and then using hoops to cover it, and then covering that back up. And here's what the main ring looked inside. The reason for this plastic is that, as with many Bob Wilson constructions, the roof leaked. And so the magnets, which have plenty of problems on their own because they were really working to a tight budget and being exceptionally frugal, the magnets got wet and waterlogged and things like that. So the year before they got the machine to work, I was not a member of the Fermilab staff, but I'm told that it was the longest year in the life of many people who were doing that. But there was an end, and on February 12th, early in the morning, in 1972, they managed to accelerate the beam of protons up to just over 100 billion electron volts. The previous world record was held by a machine in Protvino in the Soviet Union, which was 76 billion electron volts, so there was great celebration for having seized the world record. And in a nice touch, some of our colleagues from the Soviet Union contributed a bottle of vodka extra, which was drunk in the control room on the occasion of this. Now, on that very night, at 4 in the morning, the first experimental events were recorded. And this is a very interesting collaboration. This was in 1972. Richard Nixon and Leonid Brezhnev were the leaders of the two superpowers. They were both pretty tough characters. Nevertheless, they thought that it would be nice to encourage cooperation between the two superpowers, rival superpowers, in an area which could be of no threat to anybody, namely particle physics. So that was our good fortune. And through the friendships of some of our colleagues on this side and on the other side, one of the first collaborations formed was this one from the Soviet Union, the Joint Institute for Nuclear Research in Dubna, and from a number of American institutions, including Fermilab. They had the clever idea that, it was one thing to accelerate the protons to high energy. It would be another trick to actually get them out of the machine so you could do experiments. So they resorted to an old technique, which was intercepting the beam as it was circulating in the ring. And they did this with a thing that was a little motor that could turn at 3,600 revolutions per minute. On this was a polyethylene foil, specially shaped, and so it went around and around like that. It would intercept the beam, and they could detect particles that were scattered by this very thin target, so thin that it wouldn't bother too much, wouldn't absorb too many of the beam particles. And so they took their first data that very first night that the accelerator reached 100 GeV. I've now seen a photo of the prototype of their little apparatus, and I did a little research, discovered that the prototype was made in 1970. In 1971, someone else invented the weed whacker, and if they'd been a little faster to bring their invention to market, we could have paid for the rest of the experimental program. But they were focused on the physics. Later on, they added a new feature, which was to send a supersonic jet of hydrogen gas through the beam. That was even better, even more tenuous beam. And because they were inside the accelerator, they could actually make measurements as the beam energy increased during the acceleration process. So that was a very nice piece of work, and it was wonderful on the day the accelerator began to work to get some data. Within a couple of weeks, by the beginning of March, thanks to twiddling with some dials in the radio frequency building, the design energy of 200 GeV was reached, and that was cause for the celebration, not with vodka, but with some unknown liquid this time. Oh, for the days of Dixie cups. Now, the first experiment to actually publish data came from this device called a bubble chamber. So this was a 30-inch in diameter device under pressure of superheated liquid hydrogen. so that when charged particles fly through it and you relieve the pressure, a chain of bubbles forms. They look like this. This was brought to us by people from Argonne National Laboratory. And I don't know if this is an early example of product placement or what in the right corner there. So the bubble chamber pictures are iconic and wonderful because they give you, when you take stereo views, three-dimensional views of the particles. It's a little clunky in the sense that it's slow, and you see a picture is there forever, but then you digitize the picture, so it's real physics to analog to digital and back and forth. But they are beautiful and they're iconic. And we were all so taken by these when they first came because it was the first step into a new energy regime that we just wanted to collect these pictures. I remember Richard Feynman coming here and wanting to take home a sheaf full of bubble chamber pictures because it was our first look at many particles, many was 10 in those days, being produced. Here's another one of those images. So they actually produced the first publication. Here's a scanning table showing one of our scanners looking at the bubble chamber pictures. They would be projected on a very flat table, and then either using curved pieces of plastic or later on by being able to digitize them with electronic devices, one could measure the trajectories of the particles coming out. So they submitted on the 21st of July, and this was published in the journal Physical Review Letters, the first experimental publication from Fermilab. What they did here was a stupendously simple thing. They simply counted the number of pictures they had, in which there were 2 particles coming out, or 4 particles coming out, or 6 particles coming out. So easy stuff. You've got to get the efficiencies right. Nevertheless, by looking at this, and then by some more complicated things, more sophisticated things that they and their competitors at other energies did in the succeeding months, we were able to learn lessons about how particles are produced out of the concentration of energy that comes about in these collisions that still hold today as our paradigm for the way particles are produced. And it was all because this is such a visual and revealing medium for doing experiments. That same summer, at the end of the summer, there was an International Conference of High Energy Physics. This is our biggest meeting that happens every 2 years. It was half in Chicago. There were parallel sessions at the University of Chicago where there are lots of rooms for small meetings. And then there were the plenary sessions in this auditorium, as you heard before, with the funeral director's chairs taking the place of the comfortable seats that you have now. Our artist, Angela Gonzalez, designed the covers for the 4 volumes of proceedings of this. The first 2 speak to Chicago. The second 2 speak to what was to become Fermi National Accelerator Laboratory. And this was for many people, especially from our colleagues from abroad, the first acquaintance they had with the new laboratory and the way it was working and getting started, and the first acquaintance with the Fermilab look, for which Angela was largely responsible. These many posters and covers of reports. It was, she did one for me. It was a very nice piece of work, I thought, but when I had a cover from Angela on it, I thought I'd really done something. It's one of the high points of my young career. And the other aspect of the Fermilab look, which is a collaboration between Angela and Bob Wilson, is the bright colors, the strong forms that we have around the site. And the general look of the site, again, you can see strong colors here and there, and the high-rise building in which we find ourselves toward the background. Wilson also had a brilliant act, a brilliant stroke. There's a cooling pond that you see, a canal inside the ring. That was needed to provide fresh water that would cool the magnets, the electromagnets that were steering the beam around. And he had the brilliant notion to use the dirt that was scooped up from there and put it on top of the beam, not as radiation protection, but so that if you were flying over, you could see the human beings had done something exceptional underground there. Instead of making it invisible, he wanted to make it visible. Before he hired me, he also gave me a test. He said that he learned that I came from California, not from some junior university, by the way. And so he figured I must like to ski, and he promised me that if I would come to Fermilab, he would take the dirt from the canal and build me the highest mountain in Illinois. So I'm pretty sure this was a test to see if I could estimate how high that highest building in Illinois would be, and I didn't want my name attached to it. Anyway, he did the right thing. Now, there is the matter of the high-rise, this lovely building now called Wilson Hall. Wilson was a teller of tales, and so I can only report to you what he told me, not whether it's true. He had an artistic bent, and he said while he was contemplating what to make for the laboratory building, he considered various things, campus-style buildings relating to each other, but he was much taken with the French cathedrals that can be seen from a great distance. He was reading, he says, Henry Adams' book, Mont Saint-Michel and Chartres, and that inspired him to make something here that could be seen from a great distance. So what you see back there in the mists is Mont Saint-Michel from a distance. As you approach it, it looms larger and larger and larger, and that was the model. So here is our building with this great vault in the inside. There's another story also from French cathedrals that went with Wilson's story about this building. And that was that he was fascinated by the Cathedral of Saint-Pierre in Beauvais, about an hour and a half north of France. You see it on the left. You see its great vault on the right. So it has a little resemblance to our high-rise building, but not that much. But what really fascinated Wilson about this was that it was completed at the end of the 13th century. The people who built it, the local bishop and his supporters, wanted it to be the highest Gothic cathedral anywhere, and for 4 years it was, until it fell down. It was rebuilt after an interval of a century or so, and then a much higher tower was added to it, and after 12 years, that collapsed. Wilson was a man who didn't like to over-design things. He liked to cut corners. Sometimes his things fell apart as well. So he was fascinated by the notion that you should do something impossible. And if it fell down, you'd learn your lesson and build it again. So that's the great cathedral at Beauvais. Now, one thing he didn't bring to Fermilab that I learned recently in a visit to Beauvais is in this cathedral is a fantastic astronomical clock installed in 1876. This is a very intricate mechanical computer that has 52 dials reporting various information, the phases of the moon, the position of the sun, the time of the day, the tides at Mont Saint-Michel, astronomical symbols and all of that, all done mechanically in the days before microprocessors. So if there happens to be an artistically inclined patron in the audience, I think we could use one of these to complete the analogy with, that Wilson had in mind. I want to say a few words about my colleagues in theoretical physics. Here you see my colleagues in the theory group, plus a few of the people from nearby institutions and the rest of the laboratory who regularly spend time with us. They're all brilliant, as you've already heard. But what is a particular pleasure to me, and a particular pleasure of our everyday life, is that there are at least 15 passports, 15 national origins represented in this group of people. And that partly reflects the fact that this is a great lab that attracts the best of people from all over the world. Some of them have studied in the US, some of them have studied abroad. The people who come from elsewhere enrich our experience, and then when they leave Fermilab, they are enriched by that. So that is part of my life that I value very much. What do we do? Well, what do theorists do? There's a lot of laughter, a lot of storytelling, there's a lot of coffee drinking. We make funny diagrams like this that we use to calculate things. We talk to our experimental colleagues, they bring us puzzles. We give them ideas that are sometimes brilliant and inspired and sometimes not. And the interplay between theory and experiment is one of the most satisfying things about our laboratory. Okay, now I want to turn to, we've seen a couple experimental results, but now I want to turn to Fermilab's first big discovery, the discovery of the bottom quark. Here is a proposal made by a small group of people, maybe 15 people, including Leon Letterman, who went on to become the director of the laboratory. I think this is basically the full technical content of their proposal, which is a far cry from the proposals that people make today in which they work things out. And I call your attention to point 2, search for structures in the above spectrum, publish these, and become famous. Now, I don't know the basis on which this experiment was approved, but when I was serving on the program advisory committee, occasionally there was a proposal for which the only fitting punishment was to approve them and make them do it. This may be in that category. Well, do what they did. They built this wonderful spectrometer. So back here under the floor, proton beam is coming up. It hits a target, goes through some stuff. And there are magnets that bend the particles that come out. And so you can add up their momenta and put them together. Here, I think this is the whole team when I add the two on the right that did this experiment. And they made a discovery. They found that when they added up the momenta of two muons, a mu plus and a mu minus, over a featureless background, there was this signal. It's like turning a radio dial. In some places you get a lot of interesting stuff or noise or something like that, and elsewhere you get very little. If you look at this, you can see that there are at least two separate structures. And if you look very closely, you can be induced to think that there might be three separate structures. This was enough, and they followed up, of course, with more observations, to tell us that there was a new family of particles, as it happened, made by a new set of quarks, fundamental constituents that no one had ever seen before. Now, in the way that things go, this discovery, done with great labor in 1977, is now how our colleagues calibrate their apparatus when they turn on. So Fermilab is a big participant in the CMS experiment at CERN at the Large Hadron Collider. They turn on, they run for a few minutes, or in this case for a little longer than that, and they resolve very clearly the three peaks of the upsilon family of particles. But you see now not with a few particles, a few events, but with tens of thousands in the peaks. So this is a progression from discovery to calibration. There's this third step that people worry about in which a new discovery becomes first a calibration and then a background to future discoveries. It hasn't happened very much for upsilon, but it has happened for other things that we found here at Fermilab. Okay, so let me say just a word about why this matters. Well, first, it's nice to discover a new family of particles. By comparing the spectrum of these states, which was then elaborated by other experiments, with the spectrum of states discovered only a few years before made of charm quarks, we could learn that the force between quarks is independent of the name of the quarks. That's very important and speaks to our theory of the strong interactions. The quark itself turns out to have a long lifetime on the particle scale, about a trillionth of a second. And it has been a vehicle for studying the structure of the weak interactions and learning how they put together and work, and has given rise to at least 3 accelerators being built, electron-positron accelerators. Actually, a fourth is about to come into operation now. Rewarded some theorists with a Nobel Prize for having made some conjectures about the weak interactions, and has just given rise to a whole industry of further inquiry. Okay, so that's the discovery of the upsilon or the B quark. Another thing that we started doing around the same time was to do new kinds of educational enterprises. Very early in the 1980s, we started a program of Saturday morning physics in which high school students would come here for 10 Saturdays, Saturday mornings in a row, get lectures and tours and occasional hands-on treatments. So here's one of the early classes. Another thing that happened is that some of these kids are too young to drive, and so their teachers would drive them and stay here for the lectures. So give up 10 Saturday mornings in a row for the whole morning. And we met some quite exceptional teachers in that way and discovered that we could learn quite a lot from them. Many of them have become certified master teachers and leaders of the physics teaching movement after that. So that was very instructive for us. Okay. We began a program with the Fermilab Friends of Science Education, the education office, of bringing children here for prairie tours, in which they could do hands-on things, learn from the prairie. So here are middle school students doing that. In time, we were able to build the Science Education Center, subsequently named for Leon Letterman. So here's a middle school group coming to tour the Science Education Center with their classes. Many of you may have been there on weekends. Our colleague Jerry Zimmerman, who's named Mr. Freeze, although I like to call him Dr. Freeze or Professor Freeze, has entertained and enlightened lots of people of all ages with his demonstrations of liquid nitrogen and the wonders of that. There he is, covering himself with snow. And you know, if I could get 10% of that delight from you tonight, that would be really nice. Here are kids and teachers at the Science Education Center. Fermilab people, Leon Letterman, Marge Bardeen, a few others, plus many people from the community who were looking for a way to improve science education, helped establish the Illinois Math Science Academy with state funding, the residential academy, which has at least one distinguished graduate that we've seen. Here are some kids in their new laboratories. And part of the program of IMSA is the students go off on Wednesdays to do internships. And here's a group of IMSA interns and their Fermilab mentors in the atrium. We don't neglect graduate education. Graduate students at Fermilab, so they're at other universities, but they come here to do their work, have so far deposited 2,188 PhD theses. On an earlier occasion, we actually arrayed all of them here in front of the stage. Now so many of them are coming in electronic form that it's not so impressive to show the file names. But that's a lot of PhDs that we've helped make, and a PhD is for society for 50 years. So these people are valuable to us, whatever they choose to do. Okay, I want to say some words now about the Tevatron, which was our second great accelerator. It was a dream of Wilson early on that it might be possible to go beyond the original energies. The specifications for the Fermilab machine were to reach 200 billion electron volts, which, as we saw, happened in 1972. He wanted to deliver more and eventually delivered stable running at 400 billion electron volts. That enabled, by the way, the discovery of the upsilon particle and the B quark by the Letterman group. At the original design energy, that would not have been possible, and so the higher energy benefited that. Eventually it was possible in short bursts to go up to 500 billion electron volts, but Wilson wanted to push for higher. To do so required changing technology in two ways. One was to replace the old-fashioned electromagnets in the main ring with superconducting magnets that can give you much higher magnetic fields and therefore bend in a circle particles of much higher energy. And also, because they don't heat up, don't waste electrical power by heating up the copper in the normal magnets. So if you can only make these work, it is a great benefit to building an accelerator. Well, through a lot of hard work by people here at Fermilab and elsewhere, and this goes from the people who invented the superconducting substances, niobium titanium in this case, the ones who made the strands, the cable, my colleagues here, who discovered how to make a magnet that would withstand the pressures that happen when you excite it to very, very high magnetic fields, learned how to build this machine. And it was a real tour de force on many, many accounts, allowed us to double the energy of the original machine in the same ring. Originally, we reduced the power consumption by about a factor of 3 while doubling the energy, so that was a fantastic step. Here at the top, you see the magnets of the original main ring. On the bottom, you see the magnets of the Tevatron, the superconducting machine. Wilson claimed that he had always intended to build another machine there, and that's why he left the holes in the magnet stands. He might have done it to save material and cost as well, but it was an inspired choice, however it happened. If you're going to build a superconducting machine, you have to keep the superconducting material at very low temperatures, so in our case, about 4 degrees above absolute zero. And if you're going to do that, you need a very big refrigerator. So we had, for a time, the largest helium refrigerator in the universe, run by this set of people. It's out there across from the CDF building, now called IARC. So here was the great moment at which the new Tevatron operated and reached the highest energy anybody had attained at that point, 512 billion electron volts. A lot of happiness there, a lot of relief probably as well. More celebrations. So Letterman pouring some substance. Wilson was back for the occasion and was suitably pleased. 4 of my colleagues who were particular heroes of this effort, Alvin Tolstrup on the right, who was a big driver behind making the magnets, understanding how to make the magnets, Helen Edwards, who was designed and implemented the machine with a big team of people, Rich Orr and Dick Lundy, who were in charge of manufacturing the magnets and other things. They're on the occasion here, they're dressed not for work, but because they were at the White House to receive the National Medal of Technology for their fantastic achievements. Okay, so we're accelerator builders at this laboratory. It is the National Accelerator Laboratory. And accelerators can be used not only to go to the highest energies and to do particle physics research, but for medical applications. And for a number of years, the beam for the LINAC was used when it wasn't required for other purposes to make a beam of neutrons that could be used for cancer therapy for soft tissue cancers. So on the right, looking at CAT scans, one of my colleagues who was a leader in this enterprise. On the left, showing off his six-pack abs, or abs of steel, one of our radiation technicians showing how a patient would be arrayed there. So there are a lot of people treated for soft tissue tumors using these techniques. Protons are another way of treating certain cancers, and my colleagues here built a compact proton synchrotron for the Loma Linda Hospital in Southern California, which has now treated many people for things like prostate cancer and other things, and which has given rise to the spread of proton therapy for certain kinds of cancer, including a number of centers in this area modeled on the device that they built. Okay, so what's the tevatron used for in particle physics? There are 2 ways of thinking about it. One is to use the beams of higher energy to use extracted beams and to study what happens. I want to give you 2 examples, both because they took a long time to perfect. It's maybe in the old days, maybe in high school physics lab, you go into the lab and you get an idea, or you're given an idea and you do the experiment and it works or doesn't. Often what we call experiments are institutions that live for a decade or a decade and a half or 2 decades, in which people come together pursuing some initial goals. They learn better and better how to accomplish those. They get new ideas along the way. So this is an experiment to look for the properties of what are called charmed particles, those made of the 4th quark and light quarks. And this was the second major experiment in that sequence. The first experiment had a number of near-death experiences, although it had a number of very good ideas in it and produced some intriguing initial results. But there were 2 important innovations here. One was to take advantage of a technology then being developed around the world, but really put into excellent application here, of what are called silicon microvertex detectors. These are detectors that allow you to localize the position of charged particles to a degree that was previously not possible in an electronic detector. And so that was a great advantage. These are particles that decay weakly after a lifetime that's around a picosecond, around a trillionth of a second. And so that means that even at high energies, they travel maybe a millimeter or a little bit more before falling apart. So you got to be able to look very closely. And if you want to gather large samples of them, you have to do it with an electronic detector such as this. So here's a picture of the front end of that detector. The beam comes in, there are little targets there. The targets are interleaved with the silicon microvertex detectors. And this was the first time that such techniques really led to first-rate physics results. Now, there was another challenge here, and that is that if you're taking lots of data and you have to filter out the wheat from the chaff, you have to be able to do computer processing in a way that is fast and cost-effective. Fermilab was always demanding for computing. Here are the first disk drives at Fermilab. So they're about 1 meter in diameter. I think they weighed about 1.5 tons. They spun around very fast. And the total capacity of that is that it would just hold the PDF file of my talk. But we were at the frontier. We did have online computers, PDP-11s, for data acquisition. And we did have a monster computer, a CDC 6600, which was built of basically military-grade steel. I think it could have sustained a direct hit from a howitzer and still operated. Magnetic tapes. I brought, just for your amusement, since I'm a man of a certain age, this was one of the first computer programs I wrote here at Fermilab. Which led to the discovery of the W boson, by the way. And now, well, okay. So they made all this work, and what enabled the computing was that, again, these are currents that were in the air. It was very expensive to buy computers. Mainframe computers were big, and they were not so fast, and so on. So one of my colleagues here, Tom Nash, realized that microprocessors were becoming fast enough, capable enough, you could put enough memory with them. And he and his team started building supercomputers out of little boards of microprocessors. Other people were trying similar approaches around the country and around the world. And over time, this evolved into buying boards, buying computers. We now have the huge farms of computers here at CERN, in the cloud. You know, Amazon and Microsoft and Google are in this business big time. This is one of the places that the idea started, and that people, driven by the need to analyze their data, made it work for the first time. These people also, and you'll see some of them here, together with some of my theory colleagues, built a special purpose machine for a style of theoretical computing called lattice gauge theories. It's a method of solving the theory of the strong interactions. And this has, again, led to great improvements in our ability to understand that theory and to calculate the properties of the proton and neutron and other particles. So, great achievement. So that was the first experiment I wanted to tell you about. The second is an experiment called KTEV. This is something very subtle. There are particles called kaons, hence the name of the experiment, kaons plus tevatron. And they display a slight difference in the behavior of matter and antimatter, which is very puzzling for a long time, and we didn't have all the information we needed about that. So the experiments here, again, this is one of a line of experiments. This is the culmination of a line of experiments. Similar experiments at CERN, and a nice rivalry between the two groups, trying complementary techniques. Here's one of their pieces of apparatus, a beautiful crystal calorimeter made of cesium iodide crystals. This is out in the experimental areas. Here's their control room with a bunch of them there. And this guy dressed in his underwear in the back. So they succeeded over time in comparing the behavior of matter and antimatter and finding a difference of a new kind and giving us a new insight into the way this so-called CP violation, charge parity symmetry violation, happens. And together with their friendly rivals at CERN, were able to give us a new information about that all goes into our understanding of the weak interactions as we have them today. Okay, so another interlude about Fermilab and its natural areas. One of the ideas from early days to make this a really quintessentially American laboratory was to restore the land, the condition it was in before, and that meant restoring a native prairie. So we've had people gathering seeds from the prairie plants, sorting the seeds, planting the seeds, and of course, having prairie fires. The point of the prairie fires is that the native grasses have deep roots and the invasive European species have shallow roots. So if you have a prairie fire every year, under controlled conditions, of course, you can selectively weed out the invasive species and be left with a native prairie. So there's a huge area of the inside the ring, as well as some other areas on the west end of the laboratory that have been restored to native prairie. And it is quite wonderful to see when the plants reach this high toward the end of the season. We also have, in addition to the Prairie Project, an organization now called the Fermilab Natural Areas. It's an organization of the community and Fermilab people, which takes great pleasure in the natural features of the laboratory, as well as taking care of it. Okay, the second piece of the Tevatron was to go to much higher effective energies, not by hitting protons on a target that's fixed, but by hitting a proton beam together with an antiproton beam. Now, this is a good trick. Protons come out of a bottle of hydrogen. Antiprotons don't come out of a bottle of antihydrogen, so you have to go to great lengths to make them and to trap them and to gather them into rather dense beams. This was done in a facility out to the back called the antiproton source, in which there's something called the debuncher and the accumulator, two aspects of it. So we had here at Fermilab the largest concentration of antiprotons anywhere in the world for quite a long time, and used them in two ways. One was to just take the antiprotons and collide them with a target, which might be a gas jet or something, tune the energy to make particles we wanted to. And this wonderful device that I have here is an element of a detector used for that purpose. So this is a piece of lead glass, which has wonderful properties for responding to electromagnetic radiation. My ultraviolet pointer shows you internal reflections so that it gathers all the light back to a place that you can detect it with a photomultiplier tube. It's the same material that's in your grandmother's fancy crystal, used here for detectors, and it's one of the very beautiful objects that my colleagues make. This was a spherical detector in which that's one of the elements. So that's the fixed target purpose. The real goal was, however, to make protons and antiprotons go in opposite directions around the main ring. And to do that, we had to give them directions. So the protons go this way, the antiprotons go this way. As you drove into the main ring road from just behind us, you would encounter this sign, and if you were a jogger or a blader and we wanted to be a proton, you could go to the left, and an antiproton, you could go to the right. Anyway, that is the way that they circulated. And it was fantastic technology that my accelerator colleagues developed, first to do this at all, and then to do it in such a way that they would make the beams of protons and antiprotons spiral around each other so that they only collided at the detectors where we wanted them to, and not just waste themselves on each other. There were two big collaborations. These were big collaborations in those days, 300, 400, eventually 600 or 700 people, the CDF detector. This is another illustration of the importance of international participation at Fermilab. We would not have started this detector as quickly as we did without the intense participation of Italians and Japanese physicists. They were really essential to getting it started. Others joined as we went on. And here is the so-called D0 collaboration. Again, this is around the time of the great collective discovery of these people, with a bunch of their flags shown here as well. In this very auditorium, in early 1995, there were seminars by the CDF and D0 collaborations in which they announced the discovery of the top quark. This is yet another fundamental constituent of matter. It's something that is much heavier than all the other particles. It weighs as much as an atom of, people used to say gold, but it's really osmium. Anyway, very heavy, but unlike an atom, it's not made up of lots of protons and neutrons. It's just a thing, as far as we know, has no internal structure. So great effort was required to do this. It took 10 years of serious effort at the Tevatron in order to make this happen, and it did happen right here. Here are a couple examples slightly enhanced. One event from D0. If you know how to look at this, you'll see that the two towers on the left make a W boson. A little stub up at the top makes a B quark. This line, the blue line, is a muon. That line is a neutrino that is represented by missing energy. That's another W boson, and this stuff down here is another B quark. And that was the signature of a top quark and any top quark being produced. So just a beautiful event in which you could see everything. CDF had their own microvertex detector from early days, and blowing up the vertex there, you can see the detached vertices representing two B quarks there, and the other characteristics of this event mark it as a good candidate for a top quark. So that was a big achievement, noticed by the worldwide press. In different languages, particle physics is over because it's gotten its last secret, or something like that. It's never over. So it was a beautiful thing that the two collaborations made the discovery at the same time. They made their announcement of the discovery simultaneously. But there was a little rivalry nevertheless. I wrote an article for our journal Physics Today about the top quark. And I sent the graphics editor of the journal a photograph of CDF and a photograph of D0. CDF, which is on the left, you have to admit, is more interesting graphically. And so that's what they chose. And when this appeared in the mailboxes, my D0 colleagues came to me and said, how am I going to show this to my mother? So we had to have a special run of other ones made with the D0 detector in it. Okay, another wonderful aspect of Fermilab. This was started in 1980 as our daycare center, a children's center. Here are some of the kids from recent times, cute as buttons, everyone. And here's a graduation from kindergarten or preschool or something like that at the Children's Center. It's really been a great thing for our employees and also for some of our summer visitors who come with small children. It's wonderful to have high quality care available. Okay, let's talk about another thing that we've been trying to find. We believe, on the basis of astronomical evidence and now other astrophysical evidence, that it is almost certain that what we're made of makes up only 20% of the matter of the universe, or maybe 5% of the universe all told. And the other 20% of the matter, very likely, but not certain, because we haven't found it yet, is made up of a bath of particles in which we're swimming. So particle dark matter. And if it's true that we're sort of sailing on our planet and in our solar system and in our galaxy through a sea of dark matter, then if you make sensitive enough detectors, you ought to be able to see a dark matter particle bumping into normal matter now and again. And we've had a number of efforts at Fermilab trying to do this. Here's the cryogenic dark matter search on the left using electronics semiconductor detectors. Here is a modern incarnation of the bubble chamber being used on the right. Both of these enterprises, as well as everybody else in the world, has set increasingly stringent limits on the properties of dark matter, which is not as satisfying as finding it, but is making progress nevertheless. Neutrinos have been part of the Fermilab program from the beginning. When I talked to Wilson years after he left here, he said that everything was going to be good, but he felt that neutrinos were really going to be the big stuff. A special bubble chamber, 15 feet long, was made to do neutrino physics, because you need a big target to detect these weakly interacting particles. It took pictures like the ones that we saw. Here I have a roll of the bubble chamber film. And if you look at it afterwards, and I'll roll the leader, you will see on here pictures of events induced by neutrinos and with tracks that could be interpreted. These early experiments using the 15-foot bubble chamber gave us important information about the nature of the weak interactions, especially a new kind of weak interactions called the neutral current weak interactions that were discovered in 1973 and had to be unraveled. And so were an important part of the Fermilab program. They were particularly easy to interpret, and for that reason had an advantage over some other techniques. Here's an example of one of those pictures. The reason it has all these tracks in it is that this is a mixture of helium and neon in the bubble chamber, which means that electromagnetic energy, electrons and photons, manifests itself in a jet of particles. It's easy to identify. Other neutrino experiments were done from the very beginning. The first proposal, the first approved experiment at Fermilab was called Experiment 1A. It was a neutrino experiment. Others as well. They had a number of purposes. One was to look inside the proton. The neutrino is a very good probe for doing that. The other was to study the nature of the weak interaction in various ways. Here's one of our later experiments called NUTEV. Here's the collaboration. Again, the collaboration was maybe 30 or 40 people at that time. Very large, massive detectors, lots of steel and then interleaved with detectors. And one of the classic experiments at Fermilab was to look for a new kind of neutrino called the tau neutrino. This is another one of those particles whose existence we inferred from other experiments. And we could say what its properties would be, but it's still very satisfying to show that it's really there and behaves as expected. So we thought that the tau neutrino, which we figured out how to make in a complicated way, when it interacted with normal targets, could make something called the tau lepton, a very heavy friend of the electron, which itself decays in about a trillionth of a second. And so if you could see nothing coming in, namely the neutrino, an interaction, and then a particle that decayed in the space of a few tenths of a millimeter or a millimeter, you would be able to do that. And a very effective way of doing that was to use photographic emulsion, which has very high spatial resolution. It has the disadvantage that you have to take it out and develop it before you can see what's there. And then you have to know where to look in a very small space in a very big place. And so you want to make a hybrid detector that has the ability to point back to the right place in the photographic emulsion in order to see the events. So these people, the donut experiment for direct observation of new tau, made such a detector which had emulsion targets interleaved with something called scintillating fibers, which I show you here. They respond very nicely to radiation. And then conventional detectors downstream. And they were able to find a few examples of exactly what was expected. So what you see here is some interaction. Let's look up here at the top. An interaction making a few particles, one of which goes a few millimeters actually, and then has a kink in which it's decaying into something plus neutral stuff. And these other three examples also show that. So they demonstrated for the first time that the tau neutrino was not just a figment of our imagination, but was real. And this has now developed a technique that people have used to probe the properties of neutrino oscillations, one kind of neutrino changing into others. Okay. The next step in accelerator development, both for the good of the Tevatron Collider program and for our future, current and future program in neutrinos, was to replace the main ring. It was primitive by modern standards, and also had the annoying feature that one piece of the main ring actually went through the D0 detector. So it's like having a piece of an accelerator in the liver of your detector. So it was moved to a new place, 1 pi kilometer around, just out the back. Main injector is on the bottom here, and on the top is a novel storage ring made of permanent magnets instead of electromagnets. And so with very low operating costs, quite a clever innovation. And this has allowed us not only to increase the number of protons and antiprotons that we put into the collider during the days when it was operating, which gave much greater capability to CDF and D0, and also to put unprecedented amounts of proton power onto the targets that make neutrino beams for our current round of neutrino experiments. So one of the highlights of our current program is to send neutrinos through the Earth. We bend them down by about 3 degrees, send them through the Earth, and they come out at the Sudan mine in northern Minnesota, where 2,400 feet or so underground, there is this magnificent object. The detector is there. It's about 8 meters high. So again, it's massive because neutrinos interact very little, and the flux of them reaching a distant place is small. They are lucky to have this magnificent mural in their mine site. So this experiment has told us a great deal about the properties of neutrino oscillations. We make them here mostly as muon neutrinos. By the time they arrive there, some of them have changed into electron neutrinos or tau neutrinos. And this is really on the leading edge of neutrino physics today to understand these properties. A second newer experiment, also in northern Minnesota, is called the NOVA experiment. So here it is as it's being set up. It's also in operation now. This is on the surface. It's in a building that's as long as a football field, roughly. And you can see that the detector is about 4 stories tall. So these are big detectors in order to register what's happening at the other end. Okay. So just a few words about things that we've been doing that don't involve directly terrestrial accelerators. In 1941, Pierre Auger, who was one of the founders of cosmic ray physics, wrote a book translated into English with the title, What are Cosmic Rays? My colleagues are still asking this question, even though we've learned quite a lot in the intervening time. And the contribution of Fermilab and its collaborators to this subject has been to go from sort of cottage industry experiments to really big experiments. And the really big experiment we have in mind is one that is actually conducted in Argentina. But if I put the apparatus, the array center it on Fermilab, it looks like this. So it's a considerable installation. There's 1,600 ground stations and 5 stations that look up at the sky. Here you can see a cartoon of a cosmic ray, so a proton or something coming in from way out there, interacting in the top of the atmosphere, making a shower of stuff, lots of electrons and photons and so on, muons that come down to the bottom. Those are detected in the ground stations, but then you can also look up and see the air fluorescing as the burst of energy goes through it. So that's having 2 techniques to look at these things is one of the great features in addition to the wide area that they cover in this case. Here is a Google Earth illustration. So you see a few houses over here being illuminated by muons and other things. And then the fluorescence detectors looking up and seeing a piece of track here, a piece of track there. And from that, they can reconstruct in 3 dimensions the trace of the cosmic rays and shower that came into their detector. So that's been a very productive experiment. One of the things that they've done is to measure the number of particles that reach us at stupendously high energy. At the energies they're considering, the rate of cosmic rays, primary cosmic rays, is about 1 per square kilometer per year, something like that. That's why you need a big detector and a lot of patience. And what they found is that as you go up above around 10 to the 19th electron volts, a little bit more, the flux of cosmic rays abruptly falls off. This was predicted because the universe at large is filled with cosmic microwave background radiation, the famous 3-degree radiation. And if it's really there, and we know it's there, and protons of higher energy come along, they will hit the cosmic microwave background radiation and make pions by a process called photoproduction. And so there should be a cutoff at exactly this place in the spectrum. So that almost is a proof of the cutoff is there as expected, but what remains to be shown is that there are actually sources of protons of energies higher than the cutoff would tell you. And that's the next step in the research. Another intriguing thing that they found is a change in the composition of cosmic rays as you go up in energy. It looks like they're changing from protons to heavier nuclei as you go up. That's still work in progress and hasn't been sorted out. Anyway, the industrialization of that kind of research has really led to new insights. We've done some astronomical research. So the first is the Sloan Digital Sky Survey, and I just show you why it matters to be able to do big things. Here are 500 different supernovae observed in the Sky Survey. These are then followed up for study by the Hubble Space Telescope and other instruments. Here is a couple slices of the sky showing this filamentary structure in the stuff out there, the galaxies out there, again taken from the Sky Survey. And here is our most recent astronomical enterprise, the Dark Energy Survey in Chile. Here just one little illustration of what they've been doing. They and their colleagues have discovered some things called dwarf galaxies, which are satellites of our own galaxy, but are smaller and darker than the ones we knew about before. It's an illustration that our senses are limited, our instruments are limited. When we make improvements in our instruments, we discover new things. Here, by a technique using spectroscopic information, they're able to get rid of the foreground and to see the dwarf galaxy by itself. So that's one nice little piece of work for them. Okay. So, two last things to talk about. One is our participation in the Large Hadron Collider at CERN. There have been two elements of this. One is to build pieces of the accelerator, in particular the magnets that bring the beams into small spots and give high collision rates. So a number of those were fabricated here at Fermilab by my colleagues. They look like big things, but they take a lot of meticulous work. The LHC, the Large Hadron Collider at CERN, is bigger than our machine. It's 27 kilometers around, or 17 miles around. The CERN laboratory is this little triangle. That's the LHC. It's about 100 meters underground. I always tell my friends from CERN, you know, they've got this nice little airport. We've got a much bigger airport. And they've got this cute little lake, and we've got a much bigger lake. And they have the Alps. And, you know. Anyway, there are two main experiments, and Fermilab is the United States headquarters for this CMS experiment, which lives over here. Their friendly rivals, the ATLAS experiment, lives here. And in this accelerator, which has about 7 times the energy of what our Tevatron had in its heyday, protons and protons collide head-on, and people have done great things, including, so here's the CMS detector that my colleagues participated in, big and brawny. It's 4 or 5 stories high. Lots of steel and muscle, and also superbly fine electronics that you see here in their silicon tracker. This itself is about 4 meters in diameter. And these people, as you will recall from the 4th of July in 2012, together with their colleagues at the ATLAS experiment, discovered the Higgs boson and gave us new insights into the nature of the origin of mass, the way that weak interactions work, and so on. And they have been involved in a new run of the accelerator at somewhat higher energy, the 13 TeV. Just today, our CMS colleagues are switching out some of their central tracking apparatus for a new and improved apparatus, and we expect more great things from them in the near future. Okay, what's happening at Fermilab now and in the future? We're moving on with a suite of experiments. This is from the microboon experiment, one of their first neutrino events in a new kind of detector for us to use for neutrino research. It's called a liquid argon time projection chamber. It serves in some respect as a prototype for what we hope will be the new gigantic experiments that we'll do in the future. And they're off to a running start. This gives pictures of bubble chamber aspect, but of much finer quality, telling you about the characteristic of the particles that are emitted and allowing you to say things quickly, electronically, and in great detail. So that is off to a great start. We're building muon experiments just behind us here. On the left, just behind the booster, you see the muon magnetic moment building. That's completed, and I'll show you something inside it. And then this is a somewhat old picture from last year. The building being completed next to it is for a new experiment that will look for an extremely rare, we think, disintegration of a muon into an electron, or transformation of a muon into an electron. Here is the magnetic ring for the muon magnetic moment experiment. This is a few months ago. They've done a lot of work in getting it ready for data taking. And maybe by the end of this year, or beginning of next year, they will begin taking data and give us answers after that. After that, the big deal that Fermilab has involved is to send neutrinos not just 500 miles to northern Minnesota through the Earth, but 800 miles to South Dakota, to the bustling village of Lead, South Dakota, where there will be very large underground particle detectors, and we hope to elaborate the mysteries of neutrino oscillations and other aspects of neutrino physics by doing that. So when I came here to Fermilab for the first time, I was at a university, it was a great place, a whole future before me when I came here, and this was, I soon learned, the most exciting place I could imagine being, and I'm hoping that it will be made for other young people the most exciting place to be. My colleague John Peoples, when he was director, liked to say that at Fermilab we make things and they work. And if you look at these pictures, I would amend his statement to say that our colleagues make very beautiful things and they work. Thank you very much.